The next thing we're going to look at is how the inductor's resistance to changes in current affects the actual current in a circuit. We're going to see that we have an RL circuit here, resistor and inductor. And we've got switch S1. When we close that, the battery will try and create a counterclockwise conventional current. If we close S2 and open S1, we'll find that we've got a current being sustained only by the inductor. So first we have to establish a current in the inductor. We start off with no current because the switch is open, but the moment we close the switch, the current still has to stay at zero because there can't be an instantaneous change. If there was, delta I over delta T would be infinite, and that means the EMF that the inductor produces to resist the current would be infinite, and we know that can't happen. So we start off with a current of zero, and if we wait long enough, we know that the inductor will eventually disappear from the circuit because the change in current will get so small that it's like the inductor isn't even there, and it acts like a regular piece of straight wire. So as time goes to infinity, where infinity may just take milliseconds for this to work, but as time goes to infinity, the current will go to battery EMF divided by R. We're going to get an exponential relationship on that trip from 0 to EMF over R because we're looking at the current, and the change in current is what determines the current. So again, we're going to have an exponential like we did for the RC circuit. Once we have a current established here in the middle picture that's going counterclockwise, then we open S1 at the same time we close S2, and we see that the current will not disappear immediately. What will happen is the inductor will keep the current alive, still going in the same sense as it was before here, counterclockwise, and eventually it will die off because there's nothing to power it and energy is being turned into heat in the resistor. But we start off, whatever our initial current was, we will eventually end up at zero, and that'll also be an exponential curve that connects our initial current and zero. The reason is we're going to get a differential equation when we look at the dependence of current on time in an RL circuit, just like we got a differential equation for the dependence of charge on time in a RC circuit. And again, we're not going to solve the differential equation, but we can predict we're going to get an exponential connection between the two endpoints. So we know that the current is going to go from 0 to EMF over R during the charge up phase. So the current at any time t will be EMF over R times this thing, 1 minus resistance times time over inductance. We're going to write that as 1 minus e to the negative time over tau L, where this is our inductive time constant like we had a capacitive time constant before. The inductive time constant is the inductance divided by the resistance, henries over ohms, and we know that has to give us seconds so that it can go in this exponential here. What about when we open switch 1 and close switch 2? That's this thing. We know that the current will drain away. It's going to eventually get to 0, and the formula we have then is it's whatever you started with when you opened that switch, e to the negative t over tau L. Now, if we know that an inductor and a motor are both essentially just coils of wire, we can see why if you take something like a fan, which is just a motor, and yank the plug out of the wall while it's running, you might see a spark jump back between the plug and the wall. And that's because the current went from a few amps or whatever it was to 0 very quickly, however quickly you pulled the plug out. That means the change in I per time is very large, and since L is pretty big anyway for a motor, we're going to get a very large induced EMF, and it can be big enough to exceed the dielectric breakdown strength of air, and if that happens, we get a spark.